Hi everybody, thank you so much for coming and taking the time out of your day to come see this. My name is Cyren Groisman, as he mentioned, and tonight's Planetarium show is going to be about the topic of the expansion of the universe, how it works, why it happens, and all about that. A little bit about me first. I'm 17, I'm a high school senior, as Jack mentioned. I go to Elstondale High School, which isn't too far from here. I plan on majoring in astrophysics in college, and UCLA is actually one of my top schools, so maybe somewhere in my future is giving another one of these talks. And I plan to specialize either in the study of exoplanets or in the study of the topic I'm presenting on today, the expansion of the universe. I also want to give a huge thanks to my mentor and co-host for this presentation, Jack Lubin. He's the one who introduced me. He's been integral to preparing me for this process, and I really could not be hosting this show without him. So, thank you so much. All right. So, to look at how the universe expands, we first have to look at what the universe looks like now, which is what's called the observable universe. The observable universe goes for about 13.7 billion light years, which is pretty far. And on the screen, you can actually see some photos taken by the James Webb and Hubble telescopes. On the left-hand side here, we can see a deep field image, which is essentially an image of a really large portion of space, and that image is largely comprised of galaxies and stars. You can actually identify the stars by looking for these 6 points that surround it. So there's one there, and some more scattered throughout. The 2 photos on the right are of what's called the pillars of creation, which is kind of a portion of the universe that's largely comprised of galaxies, space dust, which is made out of little particles of rock that are out in space. And the photo on the left of the pillars of creation was taken by the Hubble Space Telescope, which is not the currently used space telescope, but it's the previously used one, and it takes photos with visible light, so all the colors that you and I can see. And the photo on the right is taken by the James Webb Space Telescope, which also photographed the deep field image I was talking about previously. And the James Webb Space Telescope photographs in infrared light, so it uses kind of different heat measurements to take kind of the difference in the cold backdrop of space and the heat of stars. So now that we know what the present looks like for our universe, we can go backwards in time to kind of look at how everything started and how we got here. So this portion on the right is what we are in now, the phase we're in now. We have many galaxies, many stars, still many that are continuing to form, but we have a vast breadth of them in an incredibly large universe, and this period of time for the universe has been for the past few billion years. And prior to that, we had an earlier period where there were definitely still lots of galaxies and stars present, but not quite so many. Our universe was still kind of in more of its beginning phase of that kind of creation. And that lasted a few 100 million years, I believe so. And prior to that phase, we have really this big phase of the creation of stars and the first stars in our universe. And that really brought about the very beginnings of the galaxies that we have today, and was a much, much shorter period And you'll notice that as we move backwards in time, these periods get shorter and shorter because as there's much larger universe for these changes to occur, things happen on a much slower rate. So, our second to last slice of time is this period of really rapid expansion at the very beginning of the creation of the universe. This is when all of the particles that create stars went out into the universe, and the universe increased drastically in size from the Big Bang, which occurred right before then. The phase and time of the Big Bang lasted not even a second, to give you an idea of how quickly those kinds of things happen. And the Big Bang really just created this explosion of new space and new particles to create stars out of, and planets eventually. And now that we know what our universe looks like and what's looked like in the past, we sought out to see what's around us. And when a scientist named Hubble, who I previously mentioned as the Hubble Space Telescope is named after him because he was a really prominent figure in astronomy and astrophysics, he discovered that the universe didn't stop expanding, and that the farther away something was, the faster it was moving away from us. So we can see on the plot on the slide that the x-axis here is distance, and that is a really huge number of parsecs, and a parsec is about 3 light years for context. And to put that in like a real world perspective, 3 light years is close to the distance between our solar system and the next closest one, which is still pretty far. So this is a absolutely huge amount of distance that's measured there. And then the y-axis here is velocity, or how fast these objects are moving away from us. And you can kind of see this line that shows the correlation between a greater distance away from our solar system and a greater speed that it's moving away. And that kind of changed the entire perspective on our universe and what we think is really happening. And that led to so many discoveries in terms of how the universe is expanding and what speed it's expanding at. And to follow up with that, even though we may expect that since we all have these galaxies and all these stars, that there would be no more need for expansion, the universe is still expanding despite that. So the universe is expanding at an accelerating rate, or that rate that we're expanding at is increasing. And that is due to something called dark energy. If you look at gravity as kind of this attractive force that pulls everything in, it pulls us onto the ground of this planet, keeps us from floating off into space. Dark energy is kind of the polar opposite of that. Dark energy pushes things apart in the way that gravity pulls them together. So dark energy is what is powering this expansion and what is powering that increasing rate by pushing different objects of the universe away from each other. And we don't really know what exactly it is. And we don't know exactly why it's doing that. It's kind of one of the really big questions in this field of study right now, which, if someone were to find out, is kind of the $1 million question, because you would win the Nobel Prize in Physics for figuring it out. So a good way to look at this in a more human context is to think about a balloon. So if you start out with the balloon not being blown up yet, and it's quite small, and you were to point out, say, this galaxy here and that galaxy there, they're pretty close together as the latex of the balloon is not very stretched out yet, and there's not a great amount of distance that they can occupy or that they can be away from each other. But when someone were to slowly inflate the balloon, you can see that those two same galaxies are farther away from each other now, as the plane that they exist on has increased in size. And if you were to inflate some more, you can see that they're incredibly far apart from each other now, which is a great representation of how the expansion of the universe works. Galaxies get farther and farther away from each other as we continue to accelerate that expansion rate. And this is also a really great metaphor for it, because you can't create or destroy matter. So same as with the balloon, that at this point you still have all the same amount of balloon as you started with. It's just spread out onto a greater distance. With the same context as the universe, we started out in the Big Bang with the same amount of matter in the universe that we have now, because matter cannot be created nor destroyed. Same with energy. So with the balloon analogy, you would say is kind of being stretched. Though this isn't a completely accurate analogy, as the balloon is expanding into the air, and the universe isn't quite expanding into anything, contrary to what we might think. When we're told something is expanding, we would normally think that it's expanding into something else, expanding into the air, expanding into a different part of space, which, interestingly, is not the case. It's not quite expanding into something, more as if it is expanding on itself. Like, the capacity to have something exist in a certain place is expanding, as opposed to expanding into something pre-existing. And another good analogy for this, despite my slightly lackluster baking skills, is a cake, where you can imagine that the chocolate batter is the dark backdrop of space, and those little white chocolate chips are galaxies, solar systems, and within them, stars and planets. So we are the white chocolate chips, in a sense. And prior to baking, it has a smaller amount of distance that it can occupy, smaller amount of space that they can be away from each other. But after it's baked, and I'm not really sure what went wrong with the baking process, you can see they're farther apart. And you can see that some of the chips are here, they're there, because now we didn't create new batter. That batter is finite, just like the matter in the universe. But as it has expanded, those chips or galaxies and solar systems get farther away from each other. So, coming from what the universe looks like now and how this expansion works, we wonder what's going to happen in the future due to this expansion, and what is that going to look like for the universe. And there's kind of three main scenarios. If you look at dark energy and gravity as kind of these two warring forces in a sense, with gravity trying to draw things in and dark energy trying to push things away from each other, we kind of get these three main scenarios, one of which where dark energy overpowers gravity. The second scenario where neither one overpowers the other, and the third where gravity overpowers dark energy. And these create the three main theories of the fate of the universe. The first of these is the Big Rip. This is the scenario in which dark energy continues to accelerate the rate of expansion of the universe, and through that acceleration of that rate, eventually it will become too much for the universe to bear, and it will quite literally rip apart. This is in billions and billions of years, so not even remotely in the near future. And in the other scenario, where dark energy and gravity kind of equal out, is the Big Freeze. So in the scenario of the Big Freeze, a good analogy for that is if you have a room full of people, say a pretty small planetarium with 50 people in it, it tends to be a little warm because we as people emit heat, and all of that heat combines with each other to create a warmer environment. It's kind of the same with celestial bodies like stars and planets, but especially stars is part of their thing is emitting heat. As galaxies move away from each other, we see that they come to be farther apart, the heat interacts a lot less, and the universe will become increasingly colder. And if we reach a point where everything is so far apart from each other that the universe is so incredibly cold that it reaches the lowest possible temperature, which is absolute zero, then the universe will experience something called heat death, which is because at absolute zero, no light can exist. The laws of physics don't even properly work, and life can't exist either. It's simply too cold for any of that to happen. And so that's a second option of what might happen. And that would just be if it continues to expand with nothing else interacting with it. Our final option is the Big Crunch, which was a lot like what I depicted on there. And the Big Crunch will happen if gravity overpowers dark energy, which would occur if the rate of expansion starts to slow down at some point, and eventually that outward force of dark energy will be inferior to the inward force of gravity, and we will experience essentially a reverse Big Bang, and everything will reduce back into one single point like it was prior to that Big Bang. Now, we don't quite know which of these theories will happen and which one of these will occur, because this is an incredibly complex field of study, and it's really hard to tell what's going to happen billions and billions of years into the future while we're in the present. But if you were interested in this topic and found this interesting and think that's something you might want to study, UCLA is a great place to do that. There are many people doing research here, and if things work out, luckily, maybe me in the future. Also and one of which is Professor Tommaso Treo, who is studying this exact topic. And thank you so much for If anybody has any questions, that would be a great time to.
I had a quick question. Earlier you said that you were possibly interested in studying or specializing in exoplanets. So what would that be like? What would you, I guess, yeah. Well, I guess, so what would that be to specialize in exoplanets?
Yeah, to specialize in exoplanets, I would probably, at least for my personal interest, be working with data from the James Webb Telescope or various other telescopes used for exoplanet discovery. And I would be taking data and using that to categorize exoplanets into categories such as a super-Earth, a gas giant, things like that, and to kind of just discover planets beyond our solar system, which is what an exoplanet is, a planet beyond this solar system. So, yeah.
Of those three theories, which one do you have your money on?
Okay. Personally, I am leaning more towards the big freeze because it's looking like that acceleration is not stopping anytime soon, and I don't think it's going to be quite so extreme that we'll experience the big rip, but I don't think that it's going to stop, at least from what I've heard in like scientific findings recently.
Copy that.
I'm just wondering, is there a way to explain the difference between dark matter and dark energy? Is it the same thing?
We don't really know. It's kind of, dark energy, dark matter, all of that kind of stuff is really one of those hard to study fields in astrophysics because it's incredibly hard to study something that the definition of it is it not being there. It's hard to study something that the point of it is there's not there. So, I'm not too knowledgeable about that. I think that it's definitely a complex subject to study, so. Yeah.
So the rate that the universe is expanding is increasing, and that's because of dark matter, right? So if it's increasing, that means either three things must be true. One, dark matter doesn't obey the first law of thermodynamics. Two, dark matter is getting stronger and propelling more. Or three, it's dispersing and pushing at different places. Do you know if any of that?
Dark energy is not my specialty. I don't know all that much about it quite yet. Yeah.
So I have a question on dark energy.
Yeah,
or
go
maybe
ahead.
you'll be able to answer it. So if dark energy is the absence of something, then what implied its existence?
The existence of dark energy is because we see this like repulsive force, that there had to be a reason behind all of this expansion, and that it is kind of that opposite to gravity in the direction that it drives things. And so I think it's kind of just like that's what we found in terms of this is where this is coming from, but we don't know quite what it is at its true source.
What got you into this study?
Astrophysics as a whole, or the expansion of the universe?
Astrophysics as a whole.
I have wanted to do astrophysics since I was like 10, so it's kind of been like my life's passion. Yeah. Always wanted to study it. Always knew I was going to go into science, and just found this and I was like, oh, that's what I'm going to do.
Do you have a favorite space movie?
I liked Interstellar. It was a good one. Saw The Martian. I liked that as well. I weirdly have not seen Star Wars at all.
What?
Which is incredibly uncharacteristic for someone who likes space as much as I do. I keep saying I'll get around to it and keep not ending up doing it.
One day.
One day. Yes?
I was going to ask if you have any book recommendations.
Ooh, okay. Honestly, a lot of the reading I do is out of my physics textbook. There's a big chapter on astrophysics, and that's a lot of what I get out of there. I know that there are definitely some good ones. I think Carl Sagan wrote a bunch of books. Sorry. Suddenly losing everything I've ever read about astrophysics.
You have any last questions before we move on to part 2 of the show? Let's give Cyren another big round of applause.